Hello everyone, Grzegorz Baran here. This time I'm going to cover topic of cross-polarization. The polarization is very useful when we deal with any reflective and shiny surfaces. In practice, it is about use of this small polarization filter. We simply mount it in front of the lens to remove any glare from the picture we take while shooting any shiny or reflective surfaces. This technique works for any shiny surface type like polished wood, leather or different types of metals. It is worth to mention that this technique doesn't remove any environment reflections by itself or doesn't remove transparency. It won't do that job when we want to capture glass or any mirrors-like surfaces in a daylight. So how does the polarization works? The light is a wave of electric and magnetic fields. Most light sources like a sun, light bulbs or fire emit the light where all electromagnetic waves are oriented in different directions. If we would like to visualize that, it would look like a rain of chaotic cluttered waves. This light is unpolarized. So, as a conclusion, we can say that the light coming from a sun or bulb or candle is not polarized. The light is being polarized after it is being reflected from any reflective surface. So, when the unpolarized light hits any surface, it illuminates it. But after it bounces reflected by the surface, it is being polarized by this reflection. Reflected light can be fully polarized, but in most cases polarization from reflection is just partial. The glare we usually see is the light after it was already reflected by the surface. So, since glares come from reflections, they are partially or fully polarized and they can be blocked by polarization filter. The problem with partially polarized light is that the filter cuts just part of the light, as light which wasn't fully polarized under certain angle still passes through. The polarization filter is the basic tool for cross-polarization. It has ability to block light polarized under certain angle and this way to remove unwanted glare and reflections. This piece of glass is a circular polarization filter and is designed to be mounted on camera's lens. We can change the polarization angle by rotating it. This way we decide which light rays enter the camera lens and which don't. So, for example, since LCD monitors emit already polarized light, typically at 45 degrees to the vertical, when the polarizer axis is perpendicular to the polarization of the light from the screen, no light passes through and the polarizer appears black. It is worth to notice that we lose about at least 1 EV every time we run light through polarization filter. It is a big cost, especially in poor lighting conditions, and has to be compensated with power of light and time of exposure. The polarization filter can stop only the light rays polarized under a certain angle at the same time. Since the standard direct light isn't polarized, to make sure we have full control of which part of light passes through the filter and which not, we need to polarize it first under exact angle. In simple words, we need to bring order to all those chaotic unpolarized waves before they even hit and illuminate the surface. It can be done by introducing a second polarization filter and as a technique is called a cross-polarization. This way, to illuminate the surface, we use fully polarized under certain and constant angle light and cut all the unnecessary light waves with the second polarization filter. Hope this makes sense so far. So, to summarize, to illuminate any reflective object we want to capture and make it visible for the camera, we need a source of light. Since any standard source of light emits unpolarized light, to be able to remove reflections with the polarization filter, we need to run the light through a polarization filter which polarizes it. When the light hits the subject, it illuminates it with the light which is already polarized under a certain angle and bounces off. When it comes reflected to the camera, we run it through another polarization filter and rotate it the way we cut all speculars and glares from the illuminated surface. This way we can see pure color information without any reflective noise. Let's take a look on a few examples. First, let's take a look on open environment through polarization filter. As you can see, it doesn't change much when we look at the sky through the filter. Usually some light on the sky is partially polarized after it was reflected from atmosphere or clouds, but it is usually quite low level of polarization. Reflections on the ground from the other side comes from pure bounced light, and even if they are still just partially polarized, the polarization is way stronger. This is why the polarization filter cuts some of the glare from the wet ground surface. The other example is in controlled environment. This time as a source of light, let's use standard interior lighting. Let's grab some reflective props, the glass, aluminum foil and a stainless steel spoon. As you can see, when we look through polarization filter, we can't see any big difference. We can notice some, but they are not consistent and depend on the angle. It is because the reflected light is also just partially polarized. Also, the background brings surface reflections. It is worth to mention that many metal materials are actually very dark or even black. What we see are the environment reflections, so that silver surface we see isn't the metal surface but reflected environment. Here is another example where I use the mobile phone flashlight as a source of light. I covered the flashlight with the polarization filter to polarize it. Next, I used it to illuminate three metal props, a spoon, a knife and a scissors. This time I removed any source for surface reflections by keeping the background in darkness, so this way there was nothing metal surface can reflect. The glare was removed by the second polarization filter we looked through. This way you can see pure, physically correct color of this metal. It is black. Now it is even more obvious that what we perceive as a metal color are the just environment reflections. And this is exactly how cross-polarization works. This metal was a stainless steel. Of course, not every type of metal is black. A gold has a dark yellowish color, while real silver is a bit gray. This is an easy way to see if something is really silver or is it just a metal which mimics it. The polarization angle is defined by the angle of the surface the light hits. When the light hits any reflective surface, when bounced, it is partially self-polarized under a certain angle. Since it is polarized, it can be blocked with the polarization filter. Unfortunately, the polarization filter can cut the polarized light under a certain angle at the same time. Since usually the sun or bulb light reflected from the surface is just partially polarized, there is always some unwanted light information left under different angles. In result, the polarization filter can block just the light under a certain angle, and in practice, when we use polarization outside in a daylight, even when we use polarization, there is always some glare left. It can be fixed if we polarize the entire light by ourselves. This way, we need to eliminate any additional sources of light and use our own source of light instead. When we let this light to go through a polarization filter, in result we get the source of light which is fully polarized under exact certain angle. In these conditions, the polarization filter is able to block 100% of bounced light and remove any reflections glare we get. And this is the technique which is called a cross-polarization technique and is widely used to capture reflective surfaces without glare. Let's do another test and let's test a few other types of metals and go a bit more into details. To proceed with this test, I'm going to use my standard photometric stereo setup. Two Hoya polarizing filters. One will be mounted on the camera to filter data, while the other one will be mounted to the source of light to polarize it. As a capture background, I use Newer's round 5-in-1 multi-disc light reflector. I found this one a while ago on eBay while I was looking for a mobile background plane for photometric stereo captures. So far it works great, it's easy to carry and has 4 different background colors with white and black included. When unfolded, it creates 40 cm wide circle, which is very handy for light positioning around the subject for photometric stereo captures. For this test, I'm going to use the white color as a background. As a source of light, I'm going to use a cheap floodlight. This one has 800 lumens of visible light power. What is important with this one is that the light beam is very consistent and solid without any noise. It has 3 lighting modes. The first one is a super strong 800 lumens light. The second one is a low version of this one, and the third one is a flashing mode. Last 2 modes are totally useless, but since this light has just one button, I need to go through all of them every time I want to go back to the most powerful one. Since this lamp wasn't designed to support polarization filters, I had to improvise and find a way to improve it. The biggest issue is that the LED bulb sticks out and it isn't flat. To mount the polarization filter, I had to find a way to keep it in a distance to the bulb. So I bought a few large elastic hair bands and a duct tape. I picked the one which fits the radius of the polarization filter I was planning to use. Next, I used 2 hair bands to mount the duct tape ring and keep the polarization filter in place. Maybe it doesn't look like an engineering masterpiece, but does the job and was very cheap. Next, I set up the camera on a tripod and filled the space with different types of props. With this setup, we can proceed with the test. I put there my watch with titanium watch strap. I also put a multi-tool with titanium casing and high-quality stainless steel blade, a plastic unicorn pen painted with some cheap golden-looking paint, another stainless steel watch but with brownish metal shade, a steel spoon, a few coins, partially crumpled aluminum foil, 2 polished shiny rocks, Belgium chocolate wrapped with red tin foil, and the one naked, ready to eat, a pure silver and pure golden ring, Swarovski crystal, a big crystal with silver mount, a few more silver things I guess, and the Division 2 medal. This one is actually quite interesting since even if it's painted, it still has a few metal parts exposed. And finally the color checker as a color reference to see how we mess up with colors. And with this setup we are ready to go. Let's do the first pass with the environment light left turned on, but with the cross-polarization setup in action, just to see how the environmental reflections affect the result. As you can see, the results are inconsistent. Next, let's mount the polarization filter to the camera and rotate it to change the polarization angle we cut. As you can see, the results are still very inconsistent, mostly due to environmental light, which isn't polarized and which gives us unwanted environment reflections. Next, let's turn this light off to eliminate additional noise and use the polarized light only. Now, by rotating the polarization filter mounted on a camera, we cut all polarized light under a certain accurate and consistent angle. As you can see, all metal surfaces turns black, while silver stays silver and the gold stays golden. Looks like I need to tell my wife that silver cats are not really silver. The paint on the Division 2 medal isn't affected, but all exposed shiny metal parts, as you can see, turns black. The aluminum foil in crumpled part doesn't turn black, but I guess it's the result of reflections. I guess that light I use reflected from the white background brings some reflective noise. It probably also affects the ceiling and environment. Finally, the color checker clips keeps the color as they should. Just the frame, since it's made with shiny plastic, is being affected and lost its glare. And I think that's it with this one. I hope you enjoyed this test and polarization and cross-polarization makes more sense for you now. Of course, even if scanning any stainless steel made metal using cross-polarization technique would be pointless, as it would appear as pure black anyway, this technique is still very useful when it comes to surfaces which actually have a color information to capture. For example, it would be almost impossible to capture varnished shiny wood without cross-polarization. Here you can see how varnished wood works with this setup. It is also very useful to remove speculars from objects like leaves, rocks, fruits, vegetables, and many other things we usually struggle to capture due to their reflective nature. Also, if we capture two images with and without reflections, by subtracting them, we can isolate the specular level. Polarization and cross-polarization is a definitely very powerful tool for any captures and gives us a lot of capture possibilities when we know how to use it. It is definitely a must-have tool for photometric stereo, but I guess it's a topic for another video. I would like to mention that polarization filters are available in different forms. Those I used were designed to be mounted on camera lenses. Filters for cameras usually have higher quality to standard plastic polarization sheets. They have better transparency consistency and brings less color distortions. It matters especially for one used on the camera lens, because these values to some degree are almost irrelevant for the filter used to polarize the source of light. In case the source of light we want to polarize has totally different shape, we can use a polarization filter sheet and simply cut the shape of the choice without any concerns. Here is an example of 5 by 5 cm linear polarization sheet. As you can see, it is just a piece of elastic plastic and polarizes the light as well. Since it's linear, it polarizes wave in just one direction. In theory, there is a difference between linear and circular polarization, but for our purpose, they both give us the same result. The most important difference for us to know is that circular polarizers contain a linear polarizer that does the polarization work, but also a second layer inside the filter called a quarter wave plate, and this layer spins the light after it goes through the linear layer and before it enters the camera lens. Because, as we already know, any light bounced from reflective surface polarizes the light, this additional layer prevents double cross-polarization inside the camera, exactly on camera's mirror and beam splitters. This double inside cross-polarization might result with a black image. So if we have a mirror or other reflective surface inside our camera, a linear polarizer can cross-polarize the reflected image and possibly black out the image. For our purpose, it doesn't matter if we use a circular or linear one to polarize the source of light, but we should use a circular one for the camera lens. Of course, we can go even deeper and mess with polarization even more and introduce a third polarization filter, but I guess it would be a topic for another video. I hope you found this video informative and useful, and if you like it and want me to create and share even more content like this one, please subscribe to my channel and leave the thumbs up. Big thanks to all of you for watching and for your support. See you in the next one. Bye!